Welcome back, Algebra Express. We are in, let me move this down, Marecek 4.1. And so this is called solving systems of linear equations in two variables. And so I'm going to go back and ask the question, what does it mean to solve a system of linear equations? So we talked about single linear equations. And if I'm talking about a solution, I'm talking about something that makes the original linear equation true when I plug it in. So when I'm talking about a line, I have two variables, so it's going to be in an ordered pair, like x comma y. And I'm looking for two numbers that when I plug it in are going to make this thing true. So if I'm looking at this first one, just looking at the first equation, if I have something like 4 minus 3, I can do 2 times 4 plus a minus 3. And I'm asking, does that give me 5? So 8 minus 3 should give you 5. So this should be a solution to that first thing. So as a solution to the first linear equation, if we look at the second one, x minus 2y should look like x minus 2 times minus 3. Is that equal to 0? And again, this is this first equation, 2x plus y equals 5. That's what I'm plugging in there. This is coming from the x minus 2y equals 0. So I'm checking to see if this is a solution. 4 minus 3, is it a solution to the second one? It's not going to be a solution. 4 plus what, 6 is not equal to 10. No, is equal to 10 is not equal to 0, sorry. And so that is not true. And so this does not work for the second one. So in general, we're going to say if it doesn't work for all of them, it's not going to work for the system. So in order for something to be a solution to the system of linear equations, it has to be a solution to both of those things. So typically, they're going to give us two linear equations. I suppose we could technically probably have more. It is a system of equations, so I guess technically you could have more. But in general, if you have two unknowns, you might probably only need two equations to get at the solution, typically. So what does it say? An ordered pair is a solution to a system of equations if it satisfies both equations. I think that's what I just said. So they want us to solve this thing graphically. Okay, so first we have to graph this thing. If you want to graph 2x plus y equals 5, there might be a little bit of work that you want to do to this thing before you graph it. So we want to put it into a form that is easily graphable. So we want to move the 2x over. So I'm going to say this is y equals minus 2x plus 5. So that's the top equation. The bottom equation looks like x minus 2y equals 0, so I have to move the x over, so it should look something like what? Minus 2y equals minus x. And if I divide by negative 2 each side, this is negative, this is negative. Overall, this is going to be positive 1 over 2 x. Okay, so I have two equations I can graph. So this first equation, it's going through 5. So I'm counting 1, 2, 3, 4, 5. Hopefully I counted them right. 0, 5, and I'm going down to 1, 2 over 1. I'm going down 1, 2 over 1. And this should be my first line. So down to 1, down to 1. I can also go up 2 and left 1. So we should know how to graph these things. And I'm gonna have a different color. I can graph this other one. 1/2 x. So we don't see it here. But if we don't see it, we can always put a plus 0. So this thing is going through the origin. It is going up 1 over 2. Going through the origin is going up 1 over 2. Up 1 over 2. Down 1 left 2. It's the same thing. We drawing our line through the okay. So before I did anything, what was that point I gave you? 4 minus 3. 1, 2, 4. This point was the 4 minus 3. So if you notice that 4 minus 3 was a solution to this first equation, but it was not a solution to the second equation. So if we look at that, what does that mean? Well, solutions are the points that are on this line, is another way to say that. So 4 minus 3 was on this line, but it wasn't on that line. Okay. So then I want to know, what is the solution to the system of equations, and what does that look like graphically? So what does it look like graphically? It looks like a point that is both on this line and a point that is both on this line. Graphically, we call that the point of intersection, right? And so that is this thing right in here. That is the point 2, 1. So we have the point 2, 1. If you go and plug it back in this thing, it is a solution. So a solution should make this true, and it should also make this true. Okay, so now we want to solve the system of equations graphically. Check your solution by plugging in coordinates for x and y. Okay, so I'm looking at this thing. I want to solve this thing, x plus y equals 4. So I want to solve it for slope-intercept so that I can graph this. So the first thing I'm going to do is move that x to the left side. So y equals a minus x plus 4 is the first equation. The second equation looks like 2y. I'm going to subtract that 2x over, so it's going to be a minus 2x. X there. Okay, so this one was already solved. This one I got to do a little bit of solving. So this I divide by 2 still, and this is negative 2 over 2 is going to be a minus 1x. Okay. So we look at this thing. We have a minus x plus 4. 1, 2, 4 up here. And then we're going down 1 over 1. This is my first line. My second line is going through the origin. Another plus 0 here. And before I even graphed them, if you know, you look at your slopes and you know something about your slopes and you know something about the slopes being the same thing, you might know that those two things are going to be parallel lines. And so now we want to go back to finding a solution for this thing. So a solution for this line looks like things that are on this line. A solution for this line looks like things that are on this line. And so a solution for the system are points that are on both lines. So we want a point somewhere in this plane that's going to be on both of these lines. So I hope you're scratching your head a little bit now and saying, I don't know what this guy's trying to ask of me. We want to, these are parallel lines, they're never going to intersect. So if I ask you for a point that's on both of them, that's never going to happen, right? And so this is one of those critical cases. There's no point that's going to make it that's going to be a solution for both of them. So there's no solution here. So the first page was mostly about solving these things graphically. We plugged in points to check our solutions. But we haven't really figured out a symbolic way to solve these things yet. So there are basically two symbolic ways to solve these things. And again, this is like one of those sorts of things you don't want to be relying on your graphs or your hand graphs to do. It's not accurate, right? Graphing is not an accurate way to solve things. And so we want a more tried and true way to sort of solve things. And so we're going to have two sort of processes to get at that. One of them is the substitution method, and one of them is the elimination method. So substitution method, we've kind of been working up to like how to do this sort of thing. And it's in the name, you're going to substitute for one of your variables. So we see 3x plus 2y equals 2. And we see y equals 2x minus 6 here. And so when we substitute, there really is a sort of thing that is leading that you probably want to substitute for. So we have a single variable solved here. Y is solved for 2x minus 6. So everywhere I see a y in this first equation, I want to write 2x minus 6 instead. So if I rewrite this, I have 3x, I have plus 2. Now instead of y, I'm plugging in that other thing here. So I know this is equivalent to y. I can write this instead of y. This looks like 2x minus 6, and this equals 2. So I'm plugging this equation into this equation. Okay, so I have a little bit of distribution to do here. So 3x plus 4x minus 12. That'll probably help a little bit. There we go. Equals 2. And so I can combine some like terms. 7x with minus 12 equals 2. I can move things to the other side to solve for my x. So 7x equals 14. X equals 2. So I have solved for my x. If you get here, you've done a great job. But if you stop here, you're only going to get about half credit. So what does this thing look like? We're trying to find a solution to a system of equations. So a solution to a system of equations looks like an ordered pair. So we found our x. Now we need to find our y. And so if we want to solve, it should be a solution to this thing, and it should be a solution to this thing. So we have some options of where we want to go plugging in an x to find our y. So we could plug it into this first one, but almost always if you have like a substitution, I would use the substitution that you did. So if we plug in an x here, I'm plugging in x equals 2 to this thing. So y equals 2x minus 6. Y equals 2 times 2 minus 6. I believe this is going to give me 4 minus 6. I believe my y value is giving me a minus 2. And so if I want the solution, I should give the solution as an ordered pair of x comma y. And so this is my solution right here. And again, if I want to check the solution, a solution is something that when you go and plug it back into these equations, it should make it true. So I can do 3. I'm going to send it. 2. Check that. And check that. So those are the two things you can check to check your solution. Okay, so that is what, 3, 4. So 4, we want to do substitution again. So in this first one, we had this single variable, it solved for a single variable 1y, right? We had y solved for. So if we come and look here, we don't have that sort of same setup. So if you don't have that setup, what you want to do is get that setup. So if we have 2x plus 3y equals 6 and a minus 3x minus y equals 5, we're looking at these variables, and I'm looking at these variables and I'm asking myself, or I'm thinking to myself, I want to solve for a variable. What variable do I want to solve for here? And you could really do any variable here. You could solve for anything you want. You can solve either equation you want and plug it into the other one. But here, if I want to solve for something, well, if I solve for x here, I would end up dividing by 2 in the end. And then things are going to be halved. If I solve for this one, I'm going to have to divide by 3. Things are going to be thirds and stuff. And so there's this same thing that kind of jumps out at me. I see a 1y here. A negative 1y, but I can deal with negatives are okay. So I want to solve this thing for y. So if I want to solve the equation for y, the first thing I want to do is add 3x over. So I have a minus y here. Add 3x over. And I have a plus 5. So add 3x to both sides. I have a minus y equals 3x plus 5. I multiply everything by a negative. So y becomes positive. This thing becomes negative. This thing becomes negative. Okay. So this is one sort of like equation happening right here. I solve that equation for a single variable. Now I have y is equal to something. And so I see y here. Instead of y, I can always plug in this thing. So I'm looking at my first equation. Instead of y, I want to plug in the thing I just solved for. So I have 2x plus 3y looks like 2x plus 3 times. I don't want to put in a y. And I want to equal that to 6. So instead of y, what do I want to plug in? I want to plug in this thing, minus 3x minus 5. And so that is my substitution step. So I'm substituting in this equation for this variable into the other equation. I said that wrong, I think. This expression for this variable into this equation. Okay. I'm doing 3 times a minus 3 is going to give me minus 9x. And I'm doing 3 times a minus 5 is going to give me minus 15. This is equal to 6. So once I do my substitution step, you might notice I had 2 variables. when I do my substitution, I'm left with one variable, and then I'm just solving a single variable equation for a single variable. It's something we've done a few times already, so that's why I'm probably going a little bit quicker over it. So 2x minus 9x is a minus 7x. I'm doing minus 15 equals 6. I'm going to add the 15 over. Minus 7x equals what, 21. And then I'm getting what, x is a minus 3. And again, we solved it. We solved something. What did we solve? We got one variable for a system, a system of linear equations. For a linear equation, our solution looks like an ordered pair. So we have this x equals a minus 3. If you think about it, it should be true of this thing. It should also be true of this equation. But this equation is the same as this equation is the same as this equation. So we have some options of which equation we want to plug it in there. We got like 4 different equations there. And so ask yourself, which one would be the easiest to plug it in to solve for y? So if we do substitution, we can almost always use like this substitution step, right? And this is almost always what I'm going to do. It's the easiest one to solve for, typically, because you just have to plug in your x and do a little bit of work, and you're solved for y. So y equals, this is positive 9 minus 5, should do it 4, y equals 4. And so my solution looks like x comma y. It looks like minus 3 comma 4. Papers are just sitting there precariously about to fall, but they didn't. So success. Okay. So again, I have the solution minus 3 comma 4. I have these equations. If I want to check this thing, I can always go and plug it back into these equations. I have an x and a y. I can check and make sure these things work out. Okay, so next. We want to do elimination. Okay, do they give us notes? They don't give us any notes on how to do it, do they? Okay, so the setup for elimination is that we want to make the coefficients on one of these variables the same. So we want to make the coefficients either on the x's or on the y's. We want them to make them the same number. And so if we're looking at that, I'm thinking I want an LCM between 2 and 3. Or I want to find like my LCM between what, 3? It's not here, but I could say that's 1. And so if we were to find a least common multiple between 2 and 3, between 1 and 3, that's just 3. So if we're thinking about these things, which one would be easier to find? Probably going to go with the lower number, and that one would be the easier one here. And so we have a 2x plus 3y equals 6. And so we figured out 3 is the magic number. We want to make our coefficients, so these are our x coefficients. So we want to make our y coefficients both 3, but we want to make one negative and we want to make one positive. So we do want differing signs, but we can just multiply by negatives to get the signs. That's not going to change the actual number. It's just going to change the sign. It's a sign issue. So I want to get the number the same first. So let's look at this. This is already 3. Guess what? This one is already done. This one is 1. So what do I multiply by 1 to get to 3? I said aloud. I gotta multiply by 3. So I'm multiplying everything, each term on this side by 3. That looks like 3 times a minus 3 is a minus 9x. 3 times a minus y is a minus 3y. And then 3 times 5 is going to, ooh, wrong sign there. That should be equals 6. this should be equals, 15. That was an equation, not an expression. So let's get that equal sign on there. So 2x plus 3y equals 6, minus 9x minus 3y equals 15. So I think a lot of times people will like multiply one side, but then they'll forget this constant over here or do something silly like that. So my goal was to get one of the coefficients on one of those variables to be the same. They are the same. These are both 3y, and they are opposite signs. Like I wanted, it was kind of set up nice. That's the first problem. They're kind of setting you up. So we want to add these equations. Okay. So we're looking down. We're adding the left side to the left side. We're adding the right side to the right side. So we're not changing the inequality, right? And maybe like a little bit of justification there. If I see two things that are equal, 1 equals 1, right? All right, 2 plus 2 equals 4 is another way to do it. If I'm adding like a left side of the inequality, I get what 2 plus 2 plus 1 equals 4 plus 1. It's going to remain true, right? If I add sides of inequalities, the equality sort of property still holds. 5 is 5. 1 is 1, 2 plus 2 is 4. These are all true things I can say. So I can add entire sides of equalities, just like kind of keeping them separate. We've done this. This is the additive property. It just looks a little weird, a little different here, but it's still that additive property of what equalities, right? Now we're just throwing in like letters and making it look a little weird. But this is 2x minus 9x. Is a minus 7x. I have plus 3y minus 3y. I'm going to do it right. I guess I'm going to write it probably one time today. Equals 0y. This is equal to 6 should give you what? 21. So I have something 0y. I don't want to write that anymore. That is no minus 7x equals 3. For x, I'm going to divide by minus 7, so you might figure out x is a minus 3. Okay. So we have x is a minus 3. We are trying to solve this system of linear equations. And so now I got to step back and ask myself, did I solve the system of linear equations? Halfways. So I still got to solve for y. So I still got to plug in a minus 3 into one of these equations. And so I think I'm just going to hit with the first one. None of them really look prettier. Both probably equally. To solve for y. But it's not too bad. We plug in a minus 3 to the x. This is minus 6. 1 plus 3y equals 6. I add 6 to the other side. 3y is 12. My y is 4. So I have my x. I have my y quantity over here, 4. I want to put these things together as a minus 3 comma 4. And maybe you notice some of these numbers might look familiar. That is because I believe 5 is exactly the same as that previous problem, number 4. We just solved the same problem 2 different ways. So there's a few papers here. Okay. Yeah, it is exactly the same. Okay. We want to solve this thing using elimination. So I'm looking at the coefficient on the x. I'm looking at the coefficient on the y. And so do I want to do what I'm thinking is 2 and 3. If I do a 2 and 3, it's going to have to be 2 times 3. It's going to have to be 2 times 5. So I don't want to do 6 or 10. I'm probably going to go with 6 is the smaller one. So what I want to do is, this was my x. These would have been my y's. So I want to go with the 6x. I want to transform both of those coefficients on the x into 6. And I want to make one of them negative. I want to make one of them positive. So I have to account for a sign somewhere in there. But the key number here that I'm looking for is 6. So if I'm looking here at 3, what do I multiply 3 by to get to 6? So this one multiplied by the number 2. Multiplying left side, going to multiply the right side. We're multiplying everything here. I want to go 2 times 3x is going to give me 6x plus 2 times 2y is going to be 4y equals minus 17 times 2 is going to give me a minus 34. So that is coming from this first equation coming down on here. Now I want to look at that second equation. I'm looking at this 2x. What do I multiply by 2 to get to 6x? I gotta multiply this thing by 3. So I'm multiplying this thing by 3. I'm multiplying it by 3 left and right. The other thing is I want alternate signs. So one of these things I got to make negative. I didn't make the first thing negative. I want them to be opposite. But I'm also going to throw a negative into this thing. So this is a minus 3 times 2x is going to give me a 6x. Minus 3 times 5 is going to give me minus 15. Y minus 3 and a minus 4 is going to give me positive 12. So now I'm looking at this thing. Did I set it up for elimination? Did I do everything I needed? So I have a 6x and a minus 6x here. And when I do my elimination step, it should go to 0x. I have set that up correctly for elimination. So this thing is all set up for elimination. Let's go ahead and do it. This is giving me 0x. I have no more x's here. I have 4 minus 15y. This is minus 11y. And this is equal to minus 34 and 12. We're like subtracting these two. 22 and 0 it should be equal. And so y is equal to, what am I doing? 2. Divide by negative 11. That should give you 2. Okay. Now we're back to asking, have we solved this thing? We solved it for a variable. Y equals 2. Have I solved this thing? I need a ordered pair. So I still need to solve for my other variable. So I can plug it in here. I can plug it in here. I could plug it into one of these things, but I would typically not plug it into one of these things. They are bigger numbers. I would go back to probably one of these two equations. It should work for all of these things. So let's plug it into one of them. Let's go 2x plus 5 times 2 minus 4. I'm going to plug it into that second equation. 2x plus minus 4. X equals minus 7, I believe. Okay. And now we're going back. We're piecing this thing together. We need an ordered pair. Have my x is a minus 7. Have my y is 2. So the ordered pair looks like minus 7, comma 2. And again, going back, if I want to check this, I can plug it in. I can plug it in here. I can plug it in here. So I think this is the one we used to solve for x. So it might do better to plug it into the other one. 3 times minus 7 plus 2 times 2, is that equal to minus 17? That minus 21 plus 4, I think that should give it. I think that checks. Should definitely check. Okay. Okay, so before we even look at the next page, there are a few ways that lines can look. So if we're drawing two lines, and we're thinking about how two lines intersect, the point of intersection is the solution. There are basically three ways lines can kind of intersect. They can intersect once, and this is like we've seen a few times. We have one solution, it's the point of intersection. This is another one that we've seen. They could be parallel, which means they don't ever intersect, which means there is no solution. They're never going to intersect. And then there's a third one. So I know you can't see it here, but there's two lines here. It's the same line over itself. And so there's a little bit of vocabulary that they throw out at you. So if it has a solution, it's consistent. So I believe this is consistent. I believe this is also consistent. To be honest, I'm not very big on this vocabulary. I more want to know what the solutions are, and I want to know things like if you're doing things symbolically, if it's a contradiction or a identity. But going over this, if it has a solution, it's consistent. So these two have solutions. They should be consistent. This is inconsistent. It has no solution. This is consistent and independent. So if we think about this, this is a line, this is a line. They are two independent lines. If we look at this, this is the same line over itself. They're not their own individual beings, right? They're not independent beings. They are dependent, right? Okay. So this is student activity. So they want you to solve this by substitution. And they give you too many words. They shouldn't tell you all this stuff. So x equals 2y. So for x, I'm plug in 2y. So if I do this, 2 x, I'm plugging in 2y. Plus 6 equals 4y plus 6 equals 4y. And what I do is just subtract 4y and end up getting something like 6 equals. And this is a thing that people will leave off, but you have to put your 0 over here. 4y minus 4y is going to give you 0. Subtracting 4y in that step. So it is important to put your equal signs and put things like equal 0. Don't drop off the equal 0. Those things are really important. Okay. So what does this thing look like? 6 equals 0. I'm pretty sure it's not true. And so if it's not true, those are things that we call a contradiction. So this is a contradiction. Do you think the system of equations has no solution, an infinite number of solutions, and explain your reasoning? And so if we're looking at this thing, and we've seen things very similar to this when we're solving for single variables, this is a thing that's going to have no solution. A little bit behind, why is it going to have no solution? Because it doesn't matter what x and y we plug into this thing. What this is telling me is that there's no such x and y that we can plug in that's ever going to make this true, right? It kind of like quote unquote disappears. Our variables disappear. And so if we try to plug in an x and y into this, there's nothing we can plug in that's ever going to make 6 equal to 0. So nothing will ever make this true, and so there is no solution that I can give you that will make this true. And so therefore there's no solution. Okay. If you solve these things for y, you're probably going to get things that are parallel, right? Ooh, I might be giving y'all too much. I just forgot we're going to do this. Getting ahead of myself a little bit. But you should kind of know this already. Okay, so let's graph this thing. So before we graph it, we're going to have to solve these things for probably our slope-intercept form. So x equals 2y, I believe, is one of them. So we're going to solve for y. Y is going to be 1/2 x. So that's one of the lines we're graphing. The other thing is 2x plus 6 equals 4y. We're going to divide everything by 4, so 2/4 x plus 6/4 is going to be y. Round a little bit, so 1/2 x plus 3/2. And so this is sort of like we were saying on the previous page, we're expecting it to be parallel. So 1/2 means I'm going up 1/2, up 1/2, and I'm going through 0, 0. Going up 1/2, going down 1, left 2 is the same thing. I'm drawing those points and drawing my line. So this is my 1/2. I want to draw 1/2 x plus 3/2 each. Here, 1/2. I know I said never guesstimate like fractions, but this is 1/2 and I'm being lazy. So let's do it. Probably not the best drawn, but they're supposed to be parallel. If they're parallel, the classification, so this is coming from the previous page vocabulary, this classification for parallel was it had no solution that was an inconsistent. So the thing that they're looking for the classification here is inconsistent. And the number of solutions this thing has, this is coming from, it's going to have no solution. Okay, and now they're giving us another equation. And for this equation, they want us to do this with the other tactic that we have. So they want us to do this. They want us to do this with the elimination. So we want to set this up so that our variables are the same, have the same number coefficient, but opposite sign. So if we're setting this thing up, and when we do elimination, I didn't really state it explicitly, but all the problems we had were in this sort of form, right? They were in ax plus by equals c. And we hadn't talked a whole lot about that form, but in general, it's the form that we like to keep things in when we do elimination. I suppose you could probably do them in other forms, but this is the way that we kind of default to, and this is called standard form. So we like to put things in standard form when we do elimination, and there's some reasons behind that. It'll help you in the future. So let's start doing that. This is minus 2x plus y equals 2. is you gotta move 4x over to minus 4x plus 2y. Same equation, I'm just moving that thing over a little bit. So I have these things set up in standard form now. They're both in standard form. I'm looking at my coefficients. So do I want to look between 2 and 4? Or do I want to do between 1 and 2? I am going to pick 1 and 2. I want to make things, the least common multiple is 2. So this one, I'm going to have to multiply by 2. To make it an opposite side, I'm going to do it all in one swoop. I'm going to make this 2. So I'm multiplying this entire top thing by -2, makes it a positive for x, makes it a minus 2y, and makes this a minus 4. And so that's the top equation. The bottom equation is minus 4x plus 2y equals 4. Now I'm adding these two things down. This side is giving me 0x, it's giving me 0y. I still need to put a 0 on this side. My equal sign comes down. Minus 4 plus 4 is giving me 0. I still need to put a 0 on that side. So don't start like dropping your zeros. Like put them down there. We see this thing. Ooh. What does it say? What does your equation look like? Our equation looks like 0 equals 0, right? This is what we're solving. That's what we solve for. What does that look like? What does that mean? That looks like the thing that we call the identity. And what does that mean? How many solutions do you think this has? So what can we plug in? And again, a solution is something that's going to make things true. What can we plug in that is going to make this true? What is going to make 0 equals 0 true? And so there should be an infinite number of things that we can plug in. And maybe I should be a little more specific on this one, because there is an infinite number of solutions. And it is an infinite number of solutions because we're getting an identity. And we will graph this in just a second, and I think I can explain it probably a little better. It is an infinite number of solutions. But it's not all and everything. Not all of it. And there's a certain pattern that things have to go by, and we'll talk about it next page. So it is an infinite number, but it's not just anything and everything like when we had a single variable equation. There is a few little restrictions that we got to talk about, which we will do now. So let's graph this and we'll talk about it. So if I want to solve this, and I want to solve these equations, minus 2x plus y equals 2. We should kind of know what these things look like graphically before we even graph them. So if I'm getting an infinite number of solutions, what does that sort of look like graphically? We've talked about it in the previous page where we had all those vocabulary words. It looks like the same line going over itself. So hopefully this looks like the same line going over itself. And so if we want to graph this, we want to solve things for y equals mx plus b, slope intercept. We're going to have to move that 2x over. 2x plus 2 is what this is going to give me. This one, if I divide everything by 2, you might notice I'm getting that same equation of 2x plus 2. 1, up 2, 1, 2, 1, 1, 2, like this. This is what my line should look like. Draw it very quick. But I have one line, and just to emphasize it, let's do blue this time. I have another line like kind of going over it, right? It's like I have two lines. You really only have to draw it once if you have it like this. If I'm being honest, I'm just doing this for emphasis. And this goes back to the classification. The classification for this thing was that it was, and going back to the vocabulary words, if it's the same line over itself, these are not two separate lines, they are dependent, right? And the number of solutions a dependent thing has is there. And this is getting at what I was saying on the previous page, right? The solutions, there are an infinite number of solutions, but the solutions look like things that are on this line. And so there is going to be a sort of way that we write things, and I think I might be jumping ahead of myself a little bit here. I think we might actually not do this till the next lesson, but I'm going to throw it out there. So a little bit about how to write that is it looks like an X and Y that's on this line. So there are three different ways you could probably write this line. Make sure I got the right ones on the previous page. Minus 2x plus y equals 2. Or 2y equals 4x plus 4. So I have to throw one of these equations. An ordered pair, it looks like an ordered pair. And also know it in slope intercept form, I can throw that in as well. So those are all saying the same thing. It's three different ways to say the same thing, right? It's saying it looks like a point on this line is what this is saying. And so there's an infinite number of solutions, but it's not just any and every solution. And a little bit about that. If I pick a point, is it a solution to this system of equations? You can go and check it, plug it into these things. It is not going to work for any of these things, right? It's not a point on that line. It's not a system to that. It's not a solution to the system of equations. Okay. So it is an infinite number of solutions, but it's not just anything and everything out there. It has to look like things that are on that line. And since the line is going over itself, it intersects its entire self. And so everything on this line is a solution, is sort of what's happening here. We're looking for points of intersection, remember graphically. How does a line intersect itself? Well, it intersects itself all the way through, is sort of what's happening here, right? That's another way to think about it. So equation form, the classification, the number of solutions, and the solution set. Okay, so 0 equals 0. The classification identity, if that's what they're looking for, if you solve it symbolically, it's an identity. I think they wanted the other thing here maybe, but yeah, I went with identity. This is an identity, this is a contradiction. If you have an identity, I guess the other word you can say is dependent. A contradiction would be inconsistent. So if we have an identity, the number of solutions are infinite. If we have a contradiction, the number of solutions are none. There are no solutions. And so we think about the solution set. In general, it's going to look like an ordered pair, such that the ordered pair looks like points on a line. And if we think about the solution set here, It looks like the empty set is one way we could write it. We can also write it as maybe like empty set is just a set of brackets with nothing in it. Okay. So I believe that's the end of today's lesson. Again, these are sort of like the special case. Most of the time, right, we're going to give you, let's go back to that picture. Most of the time, we're going to give you something that is consistent and independent. One where you can find two numbers, right? We can find two numbers. X equals, I already threw away my Y equals. But we can find X equals, Y equals. You can give me an ordered pair that you can go and check. Most of the time, it's going to be two numbers. These are also things that pop up. They are legitimate problems that arise, and we also need to know how to find the solutions for these. But these are sort of like our special cases, right? Okay, so that is the end. I will see you in class soon.